about. Apparently, I have more to say about delta functions. So I think something we could talk about, right? Is this, right? So if you've got a sum, you know, delta ij, right? And then, you know, c sub I equals 1 to infinity, right? So what is this? This is, you know, delta 1j c1 plus delta 2j c2 and so forth, right? Eventually somewhere in here you got a jj, right? cj. But by definition, the Kronecker delta is what?
0 at all other places, but delta jj.
0 everywhere except for here where it's 1. So this is just cj. So in the same sense, you have integral, you know, whatever you want. I mean, and we could, here, just for the sake of being all snazzy and such, let's make this not a series, but like a double series, or what do you want to call this thing, just to make the analogy complete. The minus infinity to infinity, right? Delta of, you know, x minus x naught, f of x dx, well, that's just equal to f of x naught in the same way. So you could even use the notation delta of x comma x naught to drive the point home. It's a continuous extension of the Kronecker delta. It's another way you could think about it. And almost, I would wager that's why, I would suspect that's probably why Dirac used a delta.
Yeah, does make sense.
I mean, you read this kind of thing in like quantum mechanics. It's like they'll have a finite system where they've got a Kronecker delta, and then they'll be like, you know, continuously extend things. You swap out sums for integrals, and you know, they don't tend to emphasize how radical a change it is to switch out the delta ij for the Dirac delta. But it is quite a leap there, isn't it? All right, I'll stop again. I think that's all I got in me for in a moment.